Okay, you ready?
Yeah, I think so.
Okay, great. So the last talk of the morning is going to be given by Alexander Clifton from Emory University, and he's going to be speaking on an exponential bound for exponential Diffsequences.
All right, thank you, Frank. So I think we know what most of the words in my title mean, and I'll explain what Diffsequences are in a little bit. But first, I'll say that this work is what could be considered arithmetic Ramsey theory. So I'd like to first start with a basic slogan of Ramsey theory. So consider a group of 6 people, and each pair of people are either friends or enemies. Then you're guaranteed to have either 3 people that are all friends or 3 people that are all enemies. So we can think of this as complete randomness is impossible. And another way of looking at this is that there's 2 different types of relationships, friends and enemies. And if I only look at one type of relationship, I still have some interesting structure retained. So another core question in Ramsey theory that you can ask is, if you divide a whole into parts, is one of the parts guaranteed to retain some special structure? So to see an example of this, I'd like to start with a big, bold claim, which is that the positive integers contain arbitrarily long arithmetic progressions. But now, if I were to split them into 2 pieces, is this still true for either of the pieces? Or maybe I split them into 3 parts or 4 parts or any finite number of parts. So if I have a set partition of all the positive integers into r parts, am I guaranteed to have some part that still contains arbitrarily long arithmetic progressions? And the answer is yes. So this is a result of van der Verden from 1927. So the way it's phrased here is a little more quantitatively. So it's saying for any length k and a fixed number of parts, there is some n such that if I divide the first n positive integers into r parts, no matter what I do, one of the parts is going to have some KAP in it. So you might wonder what the smallest such n that works is. So here we define the van der Verden number, WRK. That's the smallest n, such that if I split my first n positive integers into r parts, one of the parts will contain arithmetic progression of length k. So the content of van der Verden's theorem is just that van der Verden numbers exist. And in terms of actually finding these van der Verden numbers, there's not a whole lot we know. So there's some interesting bounds that you can look up. But in terms of exact values, there's a few trivial families and a few small cases. But if you wanted to compute WRK, what could you do? So there's 2 things. You need a lower bound and you need an upper bound. Well, the general thing for finding lower bounds in Ramsey theory is I just need one counterexample. So the idea is if this is the smallest n, then I need to make sure n minus 1 doesn't work. So there needs to be some way of splitting the first WRK minus 1 integers into r parts such that none of those parts contains a length k arithmetic progression. And then for the upper bound, you just need to show that if I have this many, then no matter how I split it up, I am going to have a length k arithmetic progression all in one part. So to see an example of this, let's take a look at the simplest case, W23. Okay, I guess the simplest non-trivial case. So we want to find the smallest n such that if I split the first n positive integers into 2 parts, I'm guaranteed to have some part that contains a 3AP. So for the lower bound, we see we're going to have it more than 8, because if I split the first 8 integers into this red set 1, 4, 5, 8 and this blue set 2, 3, 6, 7, the red set doesn't have any 3APs and neither does the blue set. So 8 isn't good enough, and we'll show that I can't do a similar thing for 9. So no matter how hard I try to split 9 into 2 parts, so we can think of the 2 parts as 2 colors. So if I split the first 9 into a red set and a blue set, then no matter what I do, one of those sets is guaranteed to have a 3AP all in one color. So I'll call that a monochromatic 3AP. So our parts are our colors, and let's see this in action. So 4 and 6, well, there's 2 options. They're either the same color or they're not the same color. So let's just assume they're both red to start things off. And if they're both red, well, then I don't want 5 to be red, because that would give me 4, 5, 6 would be a red 3AP. So 5 would have to be blue. And 4, 6, 8, that's another 3AP. So 8 would have to be blue. And 2, 4, 6, that's another 3AP. If we don't want it to be all red, 2 would have to be blue. But now we notice in our efforts to avoid a red 3AP, we've gotten stuck having this blue 3AP 2, 5, 8. So if I want any chance of avoiding a monochromatic 3AP, 4 and 6 have to be different colors. So let's try again. So let's try 4 is blue, or sorry, 6 is blue, 4 is red. And because of the symmetry here, without loss of generality, we can assume 5 is also red. And now here's where we play Sudoku. So 3, 4, 5, that's a 3AP. We can't have it all be red. So 3 has to be blue. But now 3, 6, 9 forces 9 to be red. Now 1, 5, 9, we can't have that all red. So 1 is blue. 1, 2, 3, that forces 2 to be red. And now 2, 5, 8, we can't have that all be red. So 8 has to be blue. So each of these steps is predetermined by the previous actions. And now we're stuck because look at 7. If 5, 7, 9, well, if 7 is blue, then I've completed 6, 7, 8 as a blue 3AP. But if 7 is red, I've completed 5, 7, 9 as a red 3AP. So despite our best efforts to avoid 3APs, it happened anyway. So that shows that 9 is the upper bound here. So that's all I'll say about van der Waerden numbers. So instead of arithmetic progressions, what other types of arithmetic structures could we consider and try to make these van der Waerden type statements about? So here's where I define what a diff sequence is. So the rest of the talk, instead of arithmetic progressions, it's about diff sequences. So here, now it's okay if the gaps between consecutive terms are different from each other, but they have to lie in this fixed set D. So every time A2 minus A1, that's in my set D, A3 minus A2, that's in my set D. I only care about the consecutive gaps. So if like A5 minus A1 is not in my set, that's irrelevant. So just an example here. Suppose I'm talking about the powers of 2. Then this sequence here is a D diff sequence because 11 minus 3, that's the power of 2. 15 minus 11, that's the power of 2, etc. So I've got 5 gaps and I have 6 terms, so it's length 6. Now, the next definition is we want to know for which D can we say something like a van der Waerden theorem. So for that, we define this notion of R accessible. So if you partition the natural numbers into R disjoint sets, will there be some part that contains arbitrarily long D diff sequences? And more quantitatively, we can think of this as, is there some n such that if I color the first n positive integers with R colors, is there some color that contains a D diff sequence of length k? So this is what I'll call a monochromatic D diff sequence. So as an example of something that's R accessible, let's just consider D to be the set of even numbers. So I claim that this is always R accessible. So why is this the case? Well, if I have the positive integers, R is finite. So if I split it into a finite number of pieces, one of these sets is going to be infinite. So it will contain either infinitely many even numbers or infinitely many odd numbers. But that means if I have arbitrarily many numbers with the same parity that are the same color, if I take the gaps between those numbers, then they're all going to be even. They're all going to be in my set D. So that gives me arbitrarily long monochromatic D diff sequences. So now let's maybe take a look at something that's not accessible. So if D is the set of odd numbers, then this is never R accessible for any R at least 2. So if R is 2, what we can do is we can say, all my even numbers, I'm going to color them red. All my odd numbers, I'm going to color them blue. And my point is that we can't have arbitrarily long monochromatic D diff sequences. In fact, we can't even have a monochromatic D diff sequence of length 2, because as soon as I have 2 things that are the same color, they're going to have the same parity, and their difference is not going to lie in my set D of odd numbers. So hopefully we got the definition of accessible down. So essentially accessible means, can I make a van der Waerden type statement? So one more example of something that's not accessible. Let's look at the set of prime numbers. So this is not 3 accessible. And to see that, we can use a periodic coloring mod 12. So for example, 18 is 6 mod 12. So based on my coloring, 18 would get color 2. 15 would get color 3. So how come this avoids arbitrarily long D diff sequences? Well, suppose I have a really long D diff sequence that's color 1. Not going to happen because everything in color 1 is 1 mod 3. So all the gaps between elements of that diff sequence would have to be divisible by 3. but they're also supposed to be in my set of primes. So they'd have to be exactly 3. So the only way to have a D-diff sequence of color 1 is if all the differences are exactly 3. And, you can start with 1, 4, 7, and then oops, 10 is a different color. So after just 3 things, I'm stuck and I can't do any more in color 1. Color 2 and color 3, it's a similar argument. All the elements of those colors have the same parity. So if I want to have a D-diff sequence, all my gaps have to be even, but my gaps are also supposed to be prime. So my gaps are just 2, and eventually I can only do so many steps of length 2 before I get stuck, and I can't have a D-diff sequence that's monochromatic of length longer than 5. So that's for 3 colors, and that means that it's also not going to be R accessible for more than 3 colors. But what happens with 2 colors? And that is an open problem. So if you like this stuff, I encourage you to play around and try to see if the primes are 2 accessible. So I don't know that, but I do know another set that is 2 accessible is powers of 2. So powers of 2, they're 2 accessible. So that means we have a van der Waerden type theorem for the set D. So the natural question is, can we make analogs for the van der Waerden numbers? So we'd like to find the smallest n such that any 2 coloring of the first n numbers guarantees a monochromatic D-diff sequence of length k. So here are some previous results about this. So Landman and Robertson, they first introduced this problem. They have this exponential upper bound, and they use the periodic coloring because, right, you only need 1 coloring to get a counterexample for the lower bound. And they got this linear lower bound. So pretty big gap between linear and exponential. Along with some of my REU colleagues, we improved the lower bound a little bit. We got it up to quadratic, but that's still pretty big gap to have a polynomial lower bound and an exponential upper bound. So you might see where this is going from the title of the talk, but what I showed this year is we also have an exponential lower bound. So there's still a considerable gap because you see here, my exponent is on the order of the square root of k, whereas my upper bound, or Landman and Robertson's upper bound, is 2 to the k. So quite a gap there. In practice, if you compute out like the first few values or so, it does seem like this lower bound is more in tune with what's actually happening. So before I say a few words about how to prove the lower bound, I'd like to refresh how to show the upper bound. So how do we show the upper bound of 2 to the k minus 1? We can use induction. So the base case is k equals 1. And now the induction hypothesis is that within my first 2 to the k minus 1 integers, I'm guaranteed to have some monochromatic D-diff sequence A1 up through AK. So this is written in increasing order. So AK is the largest element, and they're all 1 color. So let's suppose AK is red. They're all red. So if they're all red and AK plus 1 was also red, that would extend my red D-diff sequence to length k plus 1. So I would want to make AK plus 1 blue to avoid that happening. And same deal with AK plus 2 or AK plus 4 or AK plus any power of 2. If I have some power of 2 and I add it to AK, if that number is red, I can just tack it on to make this sequence 1 longer and be all red. So that means numbers AK plus any power of 2 would have to all be blue. But that means AK plus 1, AK plus 2, all the way up to AK plus 2 to the k. Those numbers in that sequence, the gaps between consecutive members are themselves powers of 2. So in our efforts to avoid extending the red D-diff sequence to length k plus 1, we forced the existence of a blue D-diff sequence of length k plus 1. And this largest term here, AK plus 2 to the k, is at most 2 to the k plus 1 minus 1. So this completes the induction. So in the rest of the talk, I will talk about the lower bound. So how did we get the linear lower bound, the polynomial lower bound, improved to exponential? So here, we're going to use some periodic colorings. So I'm going to ditch red and blue. I'm just going to use color 1 and color 0. So the first coloring I consider has a repeating block of 1, 0. So what do I mean by that? I mean that we color according to parity. So 1 is color 1, 2 is color 0, 3 is color 1, 4 is color 0, etc. And why might this be a good strategy? Well, for starters, the gaps that we care about, the gaps in our set D are powers of 2. So we care only about powers of 2, and this has some potential because it avoids gaps of size 1. Like if I have 2 numbers x and x plus 1, they're guaranteed to get different colors. Let's take it a step further and look at the second row. So this is a mod 4 coloring. My repeating block is 1, 0, 0, 1. So everything's colored according to the remainder mod 4. So 1 is color 1, 2 is color 0, 3 is color 0, 4 is color 1, and then you repeat. So 5 is color 1, 6 is color 0, etc. And notice how we constructed this. How is this related to the previous row? Well, the first two in our block is just the 1, 0 from before. And the second half of our block, the 0, 1, that's the complement of the previous block. So by construction, this guarantees that any numbers x and x plus 2 get different colors. So we've avoided any gaps of size 2. But it's a little bit better than that. So let's take a look at this third column. So I say limits size 1. So not only do we have no gaps at all of size 2, but also if I have a monochromatic D diff sequence, so I have a diff sequence where everything's color 0 or everything's color 1, we already know that there's no gap of size 2, but also I'm going to have an upper bound on the number of gaps of size 1 I can have. And that's really going to be the key here. So we'll see a little more details on that in a bit. You can keep going with this pattern. So where does this third row come from? 1, 0, 0, 1, that's from copying the second row. And 0, 1, 1, 0, that's from taking the complement of 1, 0, 0, 1. So this gives us a mod 8 coloring. It avoids gaps of size 4. And we'll also see that it provides an upper bound on how many gaps of size 1 and size 2 that you can use in your diff sequence. So if we keep going in this manner, then for any t, we can define this periodic coloring pt that's colored based on the remainders mod 2 to the t. And how to find the repeating block of length 2 to the t, we can find it recursively by taking the previous one from pt minus 1 and then tacking on the complement to the end. So, well, let's say a short gap is anything less than 2 to the t minus 1, and a long gap is anything that's at least 2 to the t. And you'll notice I'm not saying anything at all about gaps of size exactly 2 to the t minus 1, because those don't happen anyway. Like if you look at the third row, that's P3. It avoids gaps of size 4. It avoids gaps of size 2 to the 2. So this third column here, when it says that we have a limited number of these other gaps, that's saying we have a limited number of these short gaps. And the key lemma here is to quantify that statement about having a limited number of short gaps. So actually, if I'm coloring with respect to PT and I take a monochromatic D diff sequence, then I'm limited to how many of these consecutive differences AI minus 1 are allowed to be short gaps. I have at most t squared minus t over 2. So that's just a quantitative sense of what I mean by the third column of limiting these small gaps. So in practice here, I'm not going to prove this, but I will say a few things about it. So one is that it's actually a stronger statement. It's not just that we have a limit to the number of small gaps, we have a limit to each type of short gap. There's at most 1 gap of size 1, at most 2 gaps of size 2, at most 3 gaps of size 4, at most 4 gaps of size 8, etc. So for example, if I'm talking about P2, that has a repeating block of 1, 0, 0, 1. And this lemma is saying that if I have a D diff sequence that's all one color, then there's at most 1 short gap. There's at most 1 gap of size 1. So to see this, let's suppose I'm talking about color 0. So having a gap of size 1, that's okay. It's possible that I have AI is some number that's 2 mod 4, and then I add 1. I have AI plus 1, that's 3 mod 4. That's also color 0, no problem. The thing is, once I'm at 3 mod 4, I am stuck at 3 mod 4. If I ever want to go back to being 2 mod 4, I'd have to add something that's 3 mod 4, but that's not a power of 2. So I have reached a dead end, and from this point forward, I'm stuck at 3 mod 4. So every time I have to add a multiple of 4, and that means I'm always adding a long gap. So since we have a upper bound on the number of short gaps, we have a lower bound on the number of long gaps. So this gives us a lower bound for AK minus A1. So to get this, we see we have at least this many long gaps, and they're at least this big. So now it seems like I may have lied to you because I promised an exponential bound in terms of K, but this just looks like it's linear in terms of K. But the catch here is that for any T, we can use a different coloring PT. So we get a family of linear lower bounds, and you can strategically pick T in terms of K to get the desired asymptotic. So that's it for my proof. Few other questions you could consider. Why did I only talk about powers of 2? it turns out powers of 3, powers of 4 is all very boring because r to the I is always 1 mod r minus 1. So the natural direction I'd like to go with this after this is to look at things like the floor of, say, e to the I. So I'm using powers of e, but it only makes sense to talk about integers, so I'm taking the floor. And since here we saw exponentials showed up, there's some other d-diff sequences where the analogs of van der Waerden numbers are polynomial. It's also an interesting question to think about what types of functions might we actually get. So I had something where I got a lower bound that was a power tower, so I was pretty excited about that with factorials. But then it turned out that that set wasn't accessible anyway. So power tower lower bound isn't so great when the answer is actually infinite. So another question could be, is it possible to even get something that's greater than an exponential? So thank you for coming, and I'm happy to take any questions.
Thank you. Questions? Nothing? Okay, maybe everyone's just hungry. So let's thank the speaker again. Okay, so we will begin again in 1 hour at 1 o'clock with Rachel Newton in this room. Thanks and see you soon.